Last time we discussed the fundamental theorem of line integrals, where if your vector field is the gradient of something, say the gradient of little f, well then the line integral of that vector field ends up just being little f of the endpoint minus little f of the start point of whatever your path is. So first let's look at some consequences of this. So if your vector field, again, we use the term conservative. So if your vector field is conservative, so meaning that it is the gradient of something, well, one of the things that the fundamental theorem of line integrals tells you is that line integrals in conservative vector fields, they're what we call path independent. In other words, if you have 2 points here, then it doesn't matter how you get from one point to the other. Those two line integrals along C1 or C2 are going to be the same. And again, let me emphasize, this is not true in general. There are vector fields, most vector fields, where if you go from one point to another along two different paths, you'll get two different answers. Second consequence of this is that the line integral along a closed path, well, it's going to be 0. Because if I have a closed path in a conservative vector field, then my start point and my end point are the same, which means that when I do f of the end point minus f of the start point, I just have to get 0. So vector fields that are conservative are actually really nice for line integrals. They have these very nice properties. Now the thing is, we haven't discussed yet really how you know whether a vector field is conservative. So in the example that I looked at in the last lecture, I just told you, I said, okay, well, your vector field capital F is the gradient of this function right here. But now imagine we say, okay, well, is, say, the vector field F equals negative y comma x, is that conservative? What about the vector field x squared comma y cubed? And, just somebody hands you a vector field. How do you know whether it's the gradient of something? Well, let's kind of try one of these. Let's start with this one right here. So to ask is f conservative, we're asking is big F the gradient of some little f? And remember, the gradient of little f means take the partial of some function with respect to x, and then the partial of the same function with respect to y. So what we want to know is whether negative yx can be written in this form right here, which means we're asking, is there a function little f that satisfies this system of partial differential equations? Okay, well, how do we solve a system like that, or how do we even get started? Well, if I want a function f such that its x derivative is negative y, what I can do is integrate both sides of that with respect to x. So f is going to be an antiderivative of the x derivative. And so I'm going to take the integral of negative y dx and see what I get. And so this is just a partial integral. We treat y as a constant, and so we get negative xy. Well, and then what your Calc 1 teacher always tried to make you write was plus c. But in this case, plus c has a special form, because when you integrate with respect to x, well, or maybe actually let's go backwards. When you take the derivative of something with respect to x, anything that's just a function of y gets treated as a constant. So in fact, what I really have is some function of y. Right? Any function that looks like negative xy plus a bunch of y stuff will have an x derivative which looks just like negative y. Okay, so I want something like that. I could then do the same thing with this one down here. Say, okay, well, if the partial of f with respect to y, if I want that to be x, then that means I want f to be, well, it's going to be the y integral of that y derivative. And the y integral of x is going to be xy plus, well, some function of x that I don't know. And so the goal is to find a function f that looks like negative xy plus a function of y, and at the same time looks like xy plus a function of x. But I think looking at that, it's pretty clear that that's not possible, because this mixed term that has x's and y's in it isn't the same in both of those. So it doesn't matter what function I start with, it doesn't matter what kind of y stuff I put in or what x stuff I put in, the x and sort of y parts don't match up. Okay, so was this vector field over here conservative? Well, no, it wasn't conservative. There's no way of writing this vector field as the gradient of something. Now, what we'd like to do is find maybe an easier way of knowing when something is not conservative. So let's think about that for just a minute. So suppose that your vector field f really is the gradient of some function. So it's, and let me just change the notation here. Let me write this now as f sub x comma f sub y for the x and y derivatives. And actually, maybe let's remember that for capital F, we typically call those components p and q. Right? P and q are just these ordinary functions of two variables that are kind of glued together to make the vector field f. Okay, so suppose that pq is the gradient of something. Now what happens if we take, say, the derivative of p with respect to y? Well, if p is fx, then the derivative of that with respect to y is fxy. And if I take the derivative of q with respect to x, since q is fy, I get fyx. And remember that in most cases, again, under some sort of niceness conditions, that fxy and fyx are the same by Clairaut's theorem. So if f is conservative, well, and nice enough, then the partial of p with respect to y has to be equal to the partial of q with respect to x. And in fact, it turns out that the converse is true, again, for some sort of niceness conditions. So I'm just going to be a little bit cagey about that here and say usually it's also true that if those partials are equal, well, then your vector field f is conservative. So what this does is it gives us a first test that we can use on a vector field to see whether it's conservative. And then if it is conservative, well, then you're going to end up doing something very similar to what we did up here. So let me just apply this test real quick to the vector fields that we saw. So the one that we tested was the vector field negative yx, where p, remember, is the first component and q is the second one. So the partial of p with respect to y in this case is negative 1. And the partial of q with respect to x is positive 1. And since those are not equal to each other, that means that the vector field is not conservative. On the other hand, if I try the other one that I wrote, which was f is x squared comma y cubed, well, then the partial of p with respect to y is in fact 0, and that's also the partial of q with respect to x. So it is a conservative vector field. In fact, anytime your vector field looks like just function of x and just function of y, it's going to turn out to be conservative. And it's not even that hard to find little f in that case. Little f is just the x integral of the first part plus the y integral of the second part. So I take 1/3 x cubed plus 1/4 y to the fourth. And if you take the gradient of that, you'll see that you really do get this vector field. Okay, so next time we'll start pulling everything together to see how you can use the fundamental theorem of line integrals and test whether a vector field is conservative, and then use the fundamental theorem if appropriate.